Hello, good morning, everyone. Can you hear me?
Good morning, sir.
Morning, sir.
Okay, hi, Samuel. Yes. Okay, so let's continue our lecture on the first part of the solar energy. So I think we should be around here. Okay, so this is the pyranometer. Okay, so it's used to measure the solar irradiance. Okay, so I think we are here now. Okay. Okay, so I did explain to you what is the function of the glass dome to avoid to avoid temperature change due to the convection. Okay, so we have two layers to maintain the temperature on the detector. And this detector can be the thermocouple, or they call it thermopillar, or can be the photovoltaics. Okay, and maybe when we need a thermopillar detector, they are have the different advantages and disadvantages. Okay, and you can see that here we have the bubble level over here, because these devices, pyranometer, they have the standard that you need to put it pointing upward, regardless where is the location of the sun. You keep pointing it upward will do. Okay, you can see that you have bubble level over here, and you have the adjustable feet and then feet put. So that means that you need to adjust this so that keep facing the upward. We don't care it's in the morning, in the afternoon, where the direction we want to face to get the maximum value of sunlight. We don't care. We just pointing it upward. Okay, but of course, the handheld pyranometer that we have in the lab, that's other story lah. When there's a handheld, so we will measure exact solar irradiance that we have, so that we will pointed it to the sunlight to get the exact value of the sunlight. But this one standard condition, they will just pointing upward. They don't care the direction of the sunlight. Okay. So the connector is actually connect to the computer or data storage system so that you can store the data you get over here. And you can see that we have the desiccant over here to absorb the monster, so that the monster will not stick to the glass and avoid to block the sunlight to reach the detector. Okay, so I think something like this lah. So the sun shield I explained to you before to avoid the reflection from the ground. Okay, and it will be UFO shape just because you want to reflect the light from the top to the other side, but not to the sensor, or else you something like you are focusing all the sunlight into one point. Okay, yeah, just now we talk about detector. Yeah, what's the difference between thermopillar pyranometer and photovoltaic pyranometer? So, photovoltaics is actually when you have the sunlight hit on it, it will give you the voltage reading. And this is almost instantaneous reading. Immediately, you hit on it, you will get the reading. Okay, but for this thermopillar or thermocouple pyranometer, when you have the sunlight hit on it, you will convert to temperature. Sorry, convert to heat. It will absorb the heat and give you the reading. Everything is related to heat. And you try to imagine that suddenly the day becomes cloudy. The solar irradiance will suddenly drop. But what happened to the reading in this detector? It won't suddenly drop because it still have the heat. The heat still not yet dissipated. Okay, so the response for this thermopillar pyranometer will be slower than the photovoltaic pyranometer. This is a disadvantage of the thermopillar pyranometer. It will react slower. Okay, photovoltaics will react immediately because it measures the voltage but not temperature. But thermopillar is measure the temperature. So of course, temperature will not change immediately when, for example, you're boiling the water and then you turn off the gas. So what happened to the temperature of water? It will remain at 100 degrees Celsius. Then it will drop to the room temperature for maybe half an hour later. Okay, so the response will be slower. Okay, but why we still use thermopillar? Okay, then we talk about the disadvantage of photovoltaics. Photovoltaics, as I explained previously, it will not absorb all the sunlight. Okay, so sunlight have a few spectrum. You have X-ray UV light visible light, infrared, and what. And not all of them able to convert to electricity. Not all of them able to release the electron from semicon. So it means that the measurement range will be narrowed down. Okay, so narrow by maybe just about 300 nanometer to 1000 nanometer. Okay, this is the range that the photovoltaic detector can detect. But for this thermopylae detector, what happened to this? It's just measure the heat. Whichever spectrum that can generate heat, then you can measure it. Almost all spectrum can generate heat other than radio wave, but radio wave is very, very limited. Okay, so it means that starting from X-ray until the entire visible light, infrared, all is considered as a sunlight. Okay, and this thermopylae able to measure all of them. Okay, but photovoltaics cannot because infrared not able to convert the sunlight into the electricity. So they have their advantages and disadvantages. So depends on what is the application. But I think thermopylae use widely lah. They will use more because for many cases for solar power plant, they use pyrometer just for monitoring purposes. Just monitor the solar area and they want to calculate the efficiency or what. They do not need the instant reading. Okay, just put there for maybe 2 years, 3 years, and then get the reading maybe every hour or what, something like this. Okay, but if you want to do a specific experiment, then maybe you can use the photovoltaic spirometer. The one in our lab is called a handheld pyrometer. They use photovoltaics. Okay, because you need the instant reading. You are holding the sensor, so of course you are expecting the instant reading. Okay. Okay, other than the pyrometer, we have brachyrometer. This one is actually the working concept is the same, but you can see that it's a very narrow opening, only the five angle acceptance angle. Why do they want to make it? Because they want to accept sunlight from one direction only. Okay, you see this one pyrometer, it accepts sunlight from 180 degrees. So it means that direct radiation it accepts. Diffuse radiation is also accepted. So you measure the total radiation. But for this case, it's only measure the direct radiation. So it means that your sensor must be always pointing to the sunlight, pointing to the direct sunlight. Okay, so whatever you measure here should be only the direct radiation. Okay, so you can see that we can measure the total radiation, we can measure the direct radiation alone, or we also can measure the diffuse radiation alone. Depends on what kind of setup you want. Okay, so you can see that for this epic pyrometer, we measure only the diffuse radiation. For the standard pyrometer, we measure total radiation. And for this pyrometer, we measure only the direct radiation. Okay, so you can see that this pyrometer, because you have to point it to the sun, always measure the direct beam, so that you need to have the tracking system. Because you need the sensor always pointing to the sun, so that you can get the measurement. You can see that the opening is very narrow. So your measurement must be very accurate. Okay, so it's pointing to the sun. But of course, it's keep pointing to the sun, but there is no sensor here. Whatever, they just use a calculation. We can exactly calculate where's the location of the sun at a given time, a given location. The sun is keep repeating every year. So as long as you know the date, the time, the location, then you know where's the location of the sun exactly. Okay. So this is how we measure the solar irradiance. And then we have this sunshine recorder. As I explained to you previously, we have the convection over here, and then you have the reading over here. So when the paper turns, it means that you have the sunlight. So according to this World Meteorology Association, they call it sunshine when the solar irradiance exceeds 120 watt per square meter. So I think in Malaysia, early in the morning, we already have more than 120 watt per square meter. Okay, Malaysia is quite hot. So in the day, in the noon time, it will be near to 1,000 or slightly above 1,000. Okay, so 120 watt per square meter is very less for Malaysia. Okay. Then let's move forward. Okay, this is about the solar energy harvesting. We have, in general, we can divide into two categories. One is direct usage. Direct usage, sunlight, we have the light and heat. So you can use a light to bright up your room or use a heat to heat up your room environment. Okay, but this one is not covered because too general, nothing to learn. Everyone know that the sun has the heat and has the light. Okay, and everyone know how to use it. But now, how do we convert the sunlight into electricity? Okay, in general, we have two methods. One, photovoltaics. Photovoltaics is a type of semiconductor. So when the sunlight hit on it, you will generate electron. So if you have the circuit connecting it to let the electron flow through the outside circuit, then you will generate electricity. Electricity refers to the flow of electron. So as long as you have free electron to flow, then you're able to generate electricity. Okay, this is what we call photovoltaics. And then the last one, we call steam turbine. Most of the power plants still use steam turbine, whether you use a gas as a fuel, you gas a coal as a fuel, you use a petrol as a fuel. So many of them still use a steam turbine. Steam turbine, the concept is I boil the water to generate steam. And this superheated steam have very high pressure. So you suddenly release to expose to the turbine. The pressure will push the turbine to rotate. Okay, so in this case, you will generate the power. Okay, when the turbine rotates, you will run the generator. Okay, maybe you look up here. Okay, so this one is a steam turbine system using the photo parabolic probe. This one, they have the sunlight hit on this plate, parabolic probe over here, and all of the sunlight will be pointed to the middle pipe. Okay, so the fluid in the middle pipe will be heated up, and it will increase in temperature. Okay, so then all the hot fluid will pass into the heat exchanger. Okay, heat exchanger, the function of heat exchanger is to exchange heat. Okay, because now the fluid exposed to the sunlight is hot, but the fluid you use to run the steam turbine is cold. So you want to transfer the heat from the hot fluid into the cold fluid, then you need a heat exchanger. But heat exchanger is actually the optional. Let's say the fluid inside, normally for steam turbine, as you call it steam, the fluid inside is water. Most of the case we will use water, unless a specific case that maybe we cannot reach the boiling point of water, then we will find the substitution for water. But in general, we use water because it's cheaper and easy to get. Okay, we'll use water. And this heat transfer fluid, some of the case they won't use water. Okay, maybe they use a molten fluid, molten salt. Or some of them maybe use some kind of the fluid which have the higher heat capacity. It can carry more heat. Okay, because if you use water, you heat up the water more than 100 degrees. What happens to the water? The water will start to boil and it will start to change to gas. So this piping system will experience high pressure inside. So maybe you will need to get the better pipe, or you need to have the higher maintenance cost. So for this case, let's try to find the fluid will not boil at the temperature that it can reach. It's like something like salt, molten salt. At high temperature, the salt already becomes the liquid form. Okay, you use the molten salt. Okay, so this molten salt and the water cannot mix together, or else molten salt is expensive for compared to the water. Okay, so we need a heat exchanger. But for some of the case, they don't want to use heat exchanger also can. They will use water in this as a heat transfer fluid. Both sides water, then you don't need the heat exchanger. Because of course the heat exchanger have the efficiency. Not 100% of the heat will transfer to the secondary fluid. Okay, so if both are water, we do not need the heat exchanger. We just pump the hot water to the turbine and produce heat. And you can see that we have additional heating. This one is also optional. Let's say some of the time the sunlight is not strong enough. So we need to provide additional heat so that the water will boil. Okay, but not boil at 100 degrees Celsius. You need to make the water until superheated steam. Okay, then you will create a very big pressure when you release. You can see suddenly this one is still not released. the water still very hot even at 200 degrees Celsius because there's no space for him to expand, for the water to expand. So it will remain as a water. But suddenly when you reach the turbine, it suddenly releases it. Okay, so you will have a sudden release in pressure, something like explosion, and then you will turn the turbine. Maybe something, but don't try at home. You find a closed bottle, you close it tightly, okay, and then you put in the hot water, and then you feel like it's actually expanding, okay, and then you have high pressure inside, and you suddenly release the water, you turn off, take out the cap, then the pressure will suddenly release, and then it has the force to rotate the turbine. Okay, this is how the steam turbine work. It will rotate by the steam. Okay, and then after you rotate the steam, after you push again the steam, the turbine, then the steam has less energy already. The pressure will drop already. Okay, so once the pressure drop, you need to go into the cooling tower, and after that, after water will cool down, then we repeat the cycle. So in this system, you can see that there is one contradiction over here. You are doing heating and you are doing cooling at the same time. So for the entire process, you need heating and cooling. Okay, or why? Why? The reason I want to heat it is I want to produce steam, but now why I want to cool it down? If I don't want to use cooling tower, okay, I use turbine and I directly, once cooled down, then I directly pump into the heat exchanger again. I repeat the cycle without cooling tower. Okay, here we call it cooling tower for big system, but some of the small system you can use a condenser. Condenser is mostly air coolant. This one cooling tower is mostly water coolant. Okay, like your air conditioning system, you have a condenser. Okay, but for our household use air conditioner, we have a condenser. But for the factory use one, they have a very big system one. Normally they won't use condenser, but they will have the centralized cooling tower. You can see that in our library, UC library. You can see at the side of the library, they have a cooling tower. There's a water flow down, something like this. Okay, there's a cooling tower. But if I don't use cooling tower, okay. Try to imagine that, let's say the steam go into the turbine is at 150 degrees Celsius and come out at 120 degrees Celsius. Can I directly pump the 120 degrees Celsius of steam back to the system? Definitely not. We are not able to do that. Of course, you can do that, but you are not able to recreate the pressure because the steam turbine is rotated by the pressure. So you need to condense the water first because the steam already expanded, and now you pass the expanded steam into the heat exchanger again, and you expect him to expand it for second time. It's impossible. It's already at the expanded stage. You won't expand again. So for this cooling tower, you condense the steam back into the water and then pumping back to the system. Okay, so you need to release the pressure, then you only pump back to the system so that it has the tendency to expand again, to create another pressure. But of course, the cooling tower you have to control nicely. You don't cool it until maybe room temperature. Okay, or else you want to heat it up to boiling point, then you will use a lot of energy. Okay, so this one must be controlled carefully. Let's say you maybe cool it down to 80 degrees Celsius and then you pump it back, or maybe 70. I don't know what's the exact value, but it must be in terms of rate lower than 100 degrees Celsius and pumping back. It cannot be too low. If too low, then you will spend a lot of energy to heat it up again. Okay, but the concept is just need to condense back to the water. Okay, so maybe, I don't know, here you produce heat, here you release heat. Maybe the heat you release here, can I use the heat release here in cooling tower to supply to the heat exchanger? Then this, you can see heat exchanger, we supply energy. Cooling tower, we release the energy. Can I use the energy from the cooling tower and supply back to the heat exchanger? Can or not? You get what I mean? Cooling tower, I'm releasing the heat. Heat exchanger, I'm supplying the heat. Can I use the heat from the cooling tower, supply to the heat exchanger? Ideal case is okay, definitely both are energy. One is minus energy, sorry, one is you remove the energy, one is you add in the energy. Okay, but in terms of exergy, this is not going to work. Okay, because the cooling tower, what's the temperature of the heat that you release? Maybe 16 degrees Celsius. Okay, but what's the temperature of the fluid inside the heat exchanger? Maybe 150 degrees Celsius. Both have the energy, but you are not able to use the low temperature support the high temperature. Okay, this is because of the temperature difference. You cannot do that. Of course, if you just talk about the energy, then totally no problem. Okay, that's why energy is not everything. You need to learn about the quality of energy. Okay, this is the same thing lah. Same system, solar collector, and you have the heat exchanger, and then similar lah. Huh? Okay, then the final thought of this chapter 2A. Argument that sun provide powers only during the day is countered by the fact that 70% of the energy demand is during daytime hour. At night, traditional method can be used to generate the electricity. It means that when someone promote the solar energy, they of course have someone argue that sun is not shine 24 hours. At night, you do not have sunlight. Okay, but actually, we use 70% of the energy at the daytime, and at night time we just use very minimal energy. Okay, so this actually is want to inform that solar energy is good because you have the solar energy when you need the energy. Okay, and the goal is not actually to reduce to replace fossil fuels with solar energy, but it's just to decrease our dependency on fossil fuels. We still need to study renewable energy, but we don't expect you replace the 100% of fossil fuels with renewable energy. We need both. Okay. Currently, 75% of our electrical power is generated by coal burning and nuclear power plant. And if you use solar energy, it can mitigate, it can reduce the effect of acid rain, carbon dioxide, and other impact of burning coal and counter risk associated with the nuclear energy. So if you use solar energy, we can reduce the acid rain, the greenhouse gas, and impact of burning coal, or maybe other counter risk associated with the nuclear energy. Maybe some kind of accident happened here. Okay, so this is good to explore solar energy. Okay, so next one is solar is totally pollution free, infinitely sustainable. But someone claim that solar energy, when you manufacture the photovoltaic panel, is toxic. Yes, it's true. You need to use a toxic substance, but if you control it nicely, carefully, there's none of the toxic material will leave the environment. Okay, but of course you need to control correctly and carefully lah. Okay, and this toxic material used in photovoltaics actually is also used in all our electronic devices, such as your monitor, your television, your handphone, all use the same thing. Okay, so if you don't want to use photovoltaic panel because of toxic, then don't use your monitor, don't use your handphone, don't use your television. Okay, that's all for first chapter, first part of the solar energy. Then I think we can continue just half an hour. Okay, this second part of the chapter 3 is will teach you how to calculate the location of the sun. Okay, this is really important when you are working in the solar industry. You need to know where's the direction of the sun. Where I need to put my solar panel to get most of the sunlight. Is that just pointing upward 90 degree? There's no such case. We won't put flat on the ground facing upward. You can see that most of the solar panel, they won't face. Maybe Google a bit, you can see. Okay, you can see that. I think you can see my sun. You can see that most of the panel not put flat on the ground. Okay, you can see that they have an angle. Why you want to put the angle? You can see most of them have the angle. But of course, this one they cannot have the angle because they're floating on the water. So you see, if you put on the ground, mostly they will put a little bit angle. But what is the most suitable angle and which direction to face? Because if you have angle, you want to face the north, south, east, or west. Okay, you can see. I think most of them have an angle. So now we learn this chapter so that you know which direction you want to face. Okay, let's continue. But of course, maybe some guess first before we learn this chapter. Let's say in Kuala Lumpur, Malaysia, you want to put the solar panel. Long time not. Let me take the attendance. Just according to your understanding, no need Google, no need what lah. More direct, Colombo lah. This is very big. So north, south, east, west. Let's say I give you 4 options. So pick lah, which one you think is correct. South, east. Okay. Give you 2 minutes to take the attendance. To take the attendance to answer the poll. A lot big east. If you see, let you see the summary. Okay, I think, okay. Okay, the correct answer is south. Okay, so you will know later lah. In general, because we are located at the north hemisphere, so we have to face our solar panel to the south. We won't face to the east or west because if you face to the east, you will get sunlight in the day, in the morning only. You face to the west, you will get sunlight in the afternoon only or evening. Okay, so east or west, you always face to the center when this is the solar. But we choose face to the north or south only, depends on your location. So in general, if our location is at the north hemisphere, we will face to the south. If our location is at the south hemisphere, we will face to the north. Okay, but the angle then we will learn it later lah. It's just a general guide. Okay, let's continue with this. Don't take it seriously, just for attendance, no much for that. Okay, this, okay, just starting from beginning. So right, you read it. Okay, I think similar, the power per unit, okay. This story is a power per unit area received from the sun in the form of electromagnetic radiation in the wavelength range of the measurement instrument. Okay, you can see that they need to split this one wavelength range of the measuring instrument, because until now we don't have one measuring instrument able to measure entire wavelength of the solar array. Okay, so whatever we measure is only maybe just 90 to 95% of the entire spectrum. Okay, we will ignore some for example, radio wave or X-ray. These two parts we are not able to measure. Okay. Secondly, irradiance may be measured in space or at the Earth's surface after the atmospheric absorption and stuff. Okay, so remember that in space, it means that just outside the atmosphere, we won't measure too far from the space law, of course, just outside the atmosphere. Okay, so this is the solar constant is measured according to this lah. Okay, which has a constant of 1370 watt per square meter. Okay, solar radiation vary with the Earth distance from the sun and with the appearance of the decay of sunspot. Earth distance from the sun, because as I explained yesterday, because the ellipse of this Earth rotate around the sun is actually ellipse but not circle, so that the distance will change from time to time lah. From day to day, I don't say time to time, from day to day. Okay, and you have the appearance of the or decay of the sunspot. You can see that from figure at the bottom, you can see that this is a part of the sun, and you can see that if you use a very good telescope, you should be able to see. Oh yeah, okay. I take note on this. I will take your agenda lah. Huh? Okay. Okay, we talk about this sunspot. You can see that the black spot on the sun's surface, and this is quite normal appear in the sun. And when you are facing this hot spot, the solar radiation that you receive will be lesser. Okay, because not all the surface is covered by the, not emit the heat, not emit the sunlight. Some of the surface emit lesser. Okay, so where is this hot spot come from? This is actually a temporary phenomenon. The hot spot, the sunspot location will change from time to time. Okay, this is actually the location with the lower temperature due to the strong magnetic field. Okay, remember that the entire sun is fully ionized. It's full of magnetic field. But at this location, due to certain region, they have very strong magnetic field. So it will pull down all the hydrogen, so that you have less hydrogen at this location. So when you have the less hydrogen at that location, you have less thermonuclear fusion. So you release less energy at that location. And everything is just because of the magnetic field pull down the hydrogen, so that there has less hydrogen on the surface of the sun to make this sunspot. Okay. Of course, the effect of sunspot, I don't think is very significant. Most significant part is actually distant from the sun. Okay, the sunspot, we not even can see it with our naked eyes. So I don't think the effect is very huge. Okay, the solar constant, the average amount of solar radiation received by the Earth's atmosphere per unit area. So the average is 1370 watt per square meter outside the atmosphere. Okay, the solar irradiation integrated over time is called solar irradiation. Okay, this is the solar irradiation in terms of watt per square meter. This is solar irradiation, so it should be in terms of energy unit. You can see that 1370 is in terms of watt, which is a power. Okay, this one is a solar irradiation, so it should be in terms of energy. It can be in terms of watt hour or in terms of joule. Okay. So you can see that this extraterrestrial solar irradiation means that the solar irradiation outside the atmosphere. Okay, before it go through the atmospheric scattering or filtering. Okay, you can see the value change from January, maximum at the January, go down to minimum at the June, and go up to maximum at the January, December. Okay, so it means that during January or December, we are getting closer to the sun. Okay, and in the June or July, we are getting furthest away from the sun. So supposedly the solar irradiation that we receive now should be lesser in June and July. Okay, but of course, this will not affect much on the solar irradiation because you still have location on the Earth. They still affect. But in general, for the entire Earth average, this point, June or July, we have the lesser solar irradiation. And you can see that this is actually a very pure sinusoidal graph. So supposedly you're able to represent this with the sine wave, sine equation or cosine equation. Okay. Now I don't put it here. Later I show you the equation. I don't know where's the slide. Okay. So solar irradiance is a form of electromagnetic, as I explained just now. It's traveling at the speed of light. Okay, speed of light is 3 times 10 power 8. So it just takes a few minutes for the sunlight to reach the Earth's surface. From the sun to Earth's surface, just take a few minutes, basically around 8 minutes good. And okay, something like this, a few minutes. Okay, so you can see that the equation is C equal to lambda V. C is the speed of light, lambda is the wavelength, and V is the velocity of that specific spectrum. Okay, so in other words, we have X-ray, UV, visible light, infrared, everything travel at the speed of light, but they have the different wavelength. In other words, they have the different velocity. Okay, so in this case, X-ray should have the highest velocity, it moves at fastest because they have more energy, it moves fastest. But same thing, it will experience the largest resistance on the atmosphere. So that X-ray will never reach the Earth's surface. It's already completely filtered out by the atmosphere. Okay. So so when a beam hit on the surface, part of it will be refracted, part of it will be absorbed, and the part will be transmitted through the body. So this thing is very important when we are designing the system. Whether you need the energy, you need the sunlight, or you don't need the sunlight. For example, if I want to build a building rooftop, I don't want to let the sunlight to go through my rooftop. So I need to find a rooftop with a high refractivity. So you will reflect most of the sunlight outward. So I receive less. Okay. So I don't want to absorb because if absorb, it will increase the temperature of the rooftop and indirectly will increase the room temperature. Okay, and then transmit also I don't want. I also don't want transmissivity. It means that the heat that already transferred through the rooftop and reach us, I also don't want. Okay, but when you are designing a solar panel, then it's totally different story. You need to have the high absorption rate. Okay, so the color of the panel really matter. So you can see that most of the panel will have a very dark color. Of course, not exactly black because some of the case it will be dark blue due to the material properties. You are not able to paint it with a dark coating or whatever because the photovoltaic panel itself have to face to the sun. You cannot paint it or what. But if you are using the solar thermal, which you have the pipe and then inside the pipe you have a button, then that one you can do the coating with a very dark color coating. So they can absorb most of the sunlight. Okay? And then you also want to try to reduce the reflection. Okay, and for example, you can see that most of the solar panel they have a glass cover to protect the panel from damage. Okay, so the glass cover must have very good transmissibility because you want all the sunlight transmit through the glass to reach the panel. Okay, so that here we have the if 100% sunlight reach a certain object, the refractivity plus absorptibility plus transmissibility must be equal to 1 or equal to 100%. Okay, but how they divide the portion depends on the material. Okay, I think you need to calculate this in your experiment. Yes, we talk about experiment. For mechanical and mechatronics student, we will start our first experiment briefing this week. Okay, so for mechatronics, your experiment briefing is start at 2 p.m. Okay, we see if you can complete all the briefing or not, 2 until 5. Okay, and then for mechanical, should be on Friday, 2 to 5 p.m. Okay, yeah? So remember to come mechanical and mechatronics. Okay, so let's continue. Factor affecting the solar irradiance received on the Earth. Okay, so this one we touched a little bit yesterday. Okay, so first, in general we have two things affecting the solar irradiance received on Earth's surface. One is the relative position, one is the transparency of the atmosphere. We look on the relative position first. The relative position of the surface to the sun ray, mainly the refraction due to the angle and the absorption due to the distance traveled through the atmosphere. So in other words, it's due to the distance traveled through the atmosphere. Okay, because atmosphere is a very big filter equipment to filter out the sunlight. So it really matters how much you receive according to the thickness of the filter. Okay. The second, the transparency of the atmosphere, including the composition of the atmosphere, particularly the thickness of the ozone layer, the percent of the water vapor or cloud cover, or maybe some kind of dust also will affect it. Okay. Okay, this is about distance, the relative portion of the sun to the particular surface on Earth, depends on these three locations. Let's say we talk about KL. Let's say KL, Kuala Lumpur. So what factor will affect the distance between Kuala Lumpur and the sun? First one is the latitude. Okay, you can see that latitude, this is the graph of latitude. On the equator, the latitude is 0. And you're going up north, the value will be getting less higher. Okay, and south also the same thing. For equator, 0 to 90 north and 90 south. And Kuala Lumpur is very close to equator at 3 degrees north. Okay, so this definitely will affect the solar irradiance. Depends on the direction of sunlight. Okay, direction of sunlight normally is quite close to the equator. It will change a little bit later. I will explain more. Okay, so that in other words, if my location is close to the equator, I should receive more sunlight because I'm closer to the sunlight. But if you're going upward, supposedly you will get less sunlight because your distance from the sun is getting further away. As we have North Pole and South Pole, they get less sunlight most of the time. Okay. And secondly, we have the day of the year. The day of the year is because of the entire Earth. The distance of the Earth from the sun is different for the entire year because of the orbit is ellipse like this. You can see ellipse. And it's ellipse, and you can see that from this point at January, the distance from the sun is only 147 million kilometers. But you see that when at this point, okay, at July, the distance is 152 million kilometers from the sun. That's why when you refer to the solar irradiance graph at July, you should get the less solar irradiance because distance is the furthest away from the sun. Okay, so this explains the day of the year, how it's affected. Okay, but the day of the year is referred to the entire Earth, regardless the location on the Earth. Okay, but latitude of course refer to different location. But this one, the day is for the entire Earth. The entire Earth move together. Okay, the last one is the time of the day. The time of the day, of course, in the morning, in the afternoon, in the day, daytime, the nighttime, because the Earth is self-evolved. So of course, at a different time, you receive different solar irradiance, and this is due to the distance travel through atmosphere, and sometimes you're blocked by the Earth itself. Okay, maybe you are at the behind of the Earth, so that you are not facing the sunlight. Of course, you do not receive any solar irradiance. So these are the three main factors affecting the relative position of the sun to the particular surface on the Earth. Okay. And then there is one criteria called AMS coefficient, or in short form, we call it AM. This, maybe you look on the general definition first. AM refers to the direction optical path length through the Earth atmosphere, expressed as a ratio relative to the path length vertically upward. Okay, we look on the equation. Okay, AM is actually AB over BC. AB is actual distance traveled through the atmosphere. You can see the sun's over here, point A and point B. Then you are standing on point B, and then the sun traveled through the atmosphere. The distance traveled through the atmosphere should be AB. Okay, and over the BC. BC should be the shortest distance, or is directly overhead. Okay, so in other words, when the sun is on the overhead at a certain day in the solar noon, AM will be equal to 1. Okay, because the sun is overhead, it goes through the shortest distance, so the AM will be equal to 1. And you can see that in the sunrise, what happened to the AB? Okay, BC and AB, yeah, correct. At sunrise, it almost infinity. Okay, but we are not able to measure that. So I think 4 to 6 is really good enough normally. We are not able to measure it. You can see that in the sunrise, it should be here. The sun should be here. Okay, and it's 90 degree to BC. Okay, so we are not able to measure using this equation anymore. But of course, we are not able to measure also at the sunrise. So you can see in the graph over here, they show only AM1 when it's directly overhead and AM until AM4. Okay, I think less than that is very hard to measure. More than that, it's very hard to measure. Okay, so what's the function of this AM? It's actually used in the most, you can see that commonly used to characterize the performance of solar cell under the standardized condition. All type of solar panel, you can see that they give you they will rate it or 300 watt, the output of 300 watt. This 300 watt is measured at the standard condition. Even you make in China, make in Malaysia, make in US, all use the same standard. We call it standard condition. So the standard condition for most of the solar panel is, you can see, value at standard test condition. We call it STC. So there are 3 parameters for standard test condition. The MS of 1.5. This gives the direction of the sun ray. Okay, and solar irradiance of 1000 watt per square meter, and cell temperature of 25 degrees Celsius. These are the 3 parameters that they need to say. Okay, so whenever they tell you that 300 watt, yes, the panel able to generate 300 watt of power when at this condition. If the condition is not as this, then you should get lesser or higher. Okay, but not all the solar panel specification will write MS coefficient. Solar irradiance of 1000 and cell temperature of 25 is a must. Okay, but MS is just refer to a direction of the sunlight. Because when you have the higher MS value, your solar irradiance definitely will drop. So it have the relationship between these two. So some of the manufacturers think that I give the solar irradiance, I give the cell temperature, is good enough. Okay, so this is how they write the solar panel. Okay, yeah, you can see that I don't know where I get this spec lah. You can see that maybe you can just get Panasonic lah or First Solar lah, whatever lah. So whatever type of solar panel, they will rate in this way. You can see that they have different type of solar panel, exactly the same, but they have different power output. 215 watt, 220 watt, 225, 230, 235, 240. And you can see that the watt glass tolerance plus 5. So it means that if you buy the glass here, you buy the solar panel at this range, the solar panel should give the output 215 to 220 because plus 5, 215 to 220 at this standard test condition. Then come up with one question. If you are the manufacturer, are you going to generate so much standard for your panel? If I am a manufacturer, I will make 200, 300, 400, 500, but I won't make 215, 220, 225, 230, correct? They are too close together and make it not much different. Okay, so as a consumer, I can use 215, I also can use 220. Okay, so it's actually complete to each other. But why most of the manufacturer make in this way? Why don't they make 200, 400, but they make 215, 220, 225? The reason behind is each solar cell is made from the silicon, and each of the silicon arrangement will really change the power output. So in other words, the manufacturer itself also don't know what kind of power output they will get. Okay, I manufacture 100 pieces of solar panel. All 100 pieces will give me different output, but of course in certain range. So that is mean that they make 1000 pieces of solar panel and the output range is from 215 to 240. You know what I mean? I don't know exactly the value. I need to test, I only know. At the time of manufacturer, I don't know what is the exact power output. Okay, because totally depends on the arrangement of each molecule in the silicon. And of course, it is quite random. So they're not able to exactly know how much the output, so that they'll make it this way. Especially for polycrystalline solar panel. Okay, so you have to pick. Normally, the buyer will buy at the same rate. It means that I want to buy 215, all 200 pieces that I want, I will buy 215. I won't mix them, or else it will be trouble when we connect them in series or parallel. Okay, so that's why they create this thing, but not by purpose, just by random, because they don't know how much they're able to generate. Okay, the spec there we'll go through in the other part of the chapter. Okay, so you need to be able to rate on this. What is mean by maximum power voltage, maximum power current, open circuit voltage. Okay. Okay, then we start on angle. There is a 4 to 5 angle you need to know in this chapter. You start from number 1, declination angle. Okay, in definition, the declination angle is a angle between the Earth equator to the direction of the sun. Okay, you can see that. Let's say this line is the Earth equator. The red line is the Earth equator, and then this is the sun. So the angle between the equator and the sun, we call it as the declination angle. Okay. So the Earth equator is tilted 23.45 with respect to the plane of the Earth orbit around the sun. Okay, you can see that it's tilted. It's not exactly flat, horizontal. Okay, because the angle between the Earth orbit and the Earth self-evolution is different. It's not both are exactly at the same angle. Okay, so they have a 23.45 degree difference. Okay, so we measure the angle here. We call it declination angle, which is the angular displacement of the sun ray with the plane of the equator. Yeah, you can see that concept. Okay, from the equator to the sun. This is called declination angle. And because of the equator is tilted 23.45 degree, so that the value of this declination angle will change from positive 23.45 to negative 23.45 degree every day. And this declination angle is affected by day, but it won't affected by time or location. Okay. So you can see in the graph over here, you have June 21st. June 21st, your location is over here. Okay, and the red line refers to the equator. And then you can see that the sun, the location of the sun is actually on the north of the equator. The red line is equator. So on the top of the equator is north. On the bottom of the equator is south. So the sunlight is hit on the north part of the equator. And it's almost 23.45 degree. In this case, we have the positive 23.45 degree, because you see here, north we use positive and south we use negative. Okay, so hit on east, we have 23.45 degree positive. And the earth is moving, it's rotating around the sun. So when it moves to the back of the sun, you can see that the sunlight will hit exactly on the middle of the equator. Okay, when it moves to the back, okay, the sunlight will exactly hit on the middle here. So when it hit on the middle, declination angle will be equal to 0. Okay, because the sunlight now is exactly the same line as the equator. Okay, so you get 0 at the back. And then it moves again to opposite direction over here. And you can see that now the sunlight is hit on the south part of the equator. And in this location, we have the angle of 23.45 degree to the south, or negative. Okay, so in other words, at June 21, declination angle is positive 23.45. Okay, and move to the back, maybe March 21 and September 21, you have the declination angle of 0. March and September, March is at the back, September is at the front. Okay, and then at December 21, the sunlight is hit on the bottom of the equator or sub of the equator, and the angle of declination is negative 23.45. So in this way, you can see that when sunlight hit on the top of equator, so it means that top of the equator is the north hemisphere of the Earth. The north hemisphere will experience summer because the sunlight hit on you. Okay, so you should be hotter. So you have summer and you have the longer daytime. Okay, and then when on the December 21st, same thing, the sunlight hit on the south of equator. So in other words, the south hemisphere will experience summer, and opposite on the north hemisphere, they will experience winter. Okay, of course, in the winter, the day length will be shorter because the hour of the sun hit on you will be lesser because you are not facing to the sun directly. Okay, so this is the change of the declination angle. Okay, any problem on this? The first angle, just between the angle of the equator to the sun, not affected by the location. Don't say Malaysia and Singapore and China, US different. No, all the same. Declination angle is for the entire Earth. You will get the same value. The difference only based on the day. Okay. This one may be better a bit. Okay, so the sun is over here. So this is okay. This don't be confused. The line over here represents the equator, but the line over here represents the axis, north-south axis. Okay, so if I want to draw the equator, the equator should be 90 degrees from the north-south axis, so should be here. Okay, this is the equator line. So you can see that the sunlight will hit on the bottom of the equator, which is the south hemisphere. So the north hemisphere will experience winter solstice in the December. Maybe you take one country in north hemisphere as a reference, maybe China. Okay, let's say China. China will experience winter in the end of the year, December 21. Okay, so you can see it on here. So on the top part will be have winter. Okay, and this one, winter solstice, summer solstice, depends on your location. This graph, I get it from the country on the north hemisphere. So winter solstice refer to the north hemisphere. But if you get the textbook from the south hemisphere, for example, Australia, then totally they will tell you that here is the summer solstice because they will write this according to their location, their country. Okay, but don't confuse this winter solstice for the north hemisphere, but for the south hemisphere, it will be summer solstice. That's all. Okay. That's why you can see that some of the book they will specify. This book is not able to use in whatever country, something like this, because their location is different. So the information given in that book may not be accurate on your location. So you have to state clearly. Okay, for example, US and Australia. US is north hemisphere, Australia is south hemisphere. So the value gives you is totally different. Okay. Okay, so we move up here. So we exactly hit on the equator and then move down. And then this is the equator line, which is 90 degrees to the north polar axis. So this one is a hit on the north. Okay, so north part we have the summer. So we north part of the Earth should have the summer solstice on June 21. Okay, and then here is the fall and the spring. There's not much different. There's a changing of the distance of the season. Okay, then if I draw this declination angle all over the year in the graph, it will look like this. Okay, maximum 23.45 in June. Minimum will be negative 24.5 in the December and January. And this is look like a sine wave, a pure sine wave. So in other words, I can represent this with the sine equation. So a general equation should be A sine theta, right? A is the amplitude, Sine theta, theta is the angle. So how I want to get the angle? Amplitude, of course, you know already because maximum is 23.45, minimum is negative 23.45. So the amplitude is 23.45. Okay, now we go to the inside the angle over here. This is 1 year is 365 days, and one rotation is 360 degrees. So it means that I want to divide this 365 to 360 degrees. Okay, sorry, I want to divide 360 degrees to 365 days because when I want to count, I count by day. So it means that at first day refers to 1st January. Okay, 1st January times 365 divide by times 360 divide by 365. Then I know where's the location of the declination, the location of the sun. But of course, the graph is not start from 0. And remember that sine graph is start from 0. So it means that this is not start from 0. So you need to include the phase shift. So you include the phase shift, then we add 284. So that it will start at 0. Okay, 284. I don't know where is it 284. Okay, so that it will start from 0 and give the exactly correct graph. Okay, I think it should be here. The plus 284 means that is behind, so it plus back, so it become here. Okay, 365 minus 284, you should get around this value. Okay, and this is the equation for the declination angle. It's applicable every time. And n is the number of days. And let's say this equation is a standard equation where we assume that every year has 365 days. We don't care about the 366 days where February you have 29 days. We just take as a normal. Okay, 365. Okay, because it's actually 365.25. Okay, so we just take 365 for that equation. It should be close enough. Okay, any question on the declination angle? Okay, maybe we take a short break, 5 minutes, and we'll continue with other angle. Okay?
Okay, sir.
Okay, come back at 12. Okay, so let's continue. Just checking, can you hear me?
Yes, sir.
Okay, good, thank you. Okay, so declination angle, no problem. So we go to the solar altitude angle. Okay, so solar altitude angle, or we can represent it as a alpha, is the angle of the sun ray from the horizontal plane, Earth's surface. This angle is affected by time, latitude, and declination angle. Okay, so different time you have the different value. Different latitude you have different value. Different declination angle, just now declination angle, you will have the different value. So it's affected by three different parameters. And alpha will be equal to 0 at the sunrise and sunset. And alpha will be maximum at solar noon. Maximum, I don't put alpha will be 90 at solar noon because not all solar noon will have the alpha equal to 90. Right? I should explain to you first. Okay, so what does this solar altitude angle means? Okay, this solar altitude angle is measured relative to the Earth's surface. Let's say this straight line is a Earth's surface. Okay, and you are standing here. Yeah, and the sunlight is actually, let's say sunlight is here. The sun. So the direction of the sunlight should be like this. Okay, so the angle between the direction of the sun ray to the ground, we call it alpha. Okay, yeah, so direction of the sun ray to the ground, to the surface. So we call it alpha. This is solar altitude angle. And this solar altitude angle can be measured experimentally based on the shadow line. You can see that if I'm standing here, okay, and your shadow line should be here. Okay, so this is your shadow line. And I can get tangent alpha. Okay, tangent alpha. And then the length of yourself divided by the shadow length. Then you should get an alpha. So you're able to measure alpha from time to time based on the shadow. As long as you can see the shadow, you can measure. But of course, the person standing here must be 90 degrees to the ground. Okay, so that you're able to get the trigonometry function over here. Okay, tangent alpha equal to length of the body divided by the length of the shadow. And you can see that at sunrise, the sun ray is exactly at the same line as the Earth's surface at the location. Okay, so the alpha will be equal to 0. The sunrise from the east and then go up and then go west. Okay, so at sunrise, the alpha equal to 0. Then at solar noon is here. The sunlight hit on your forehead. Okay, so that the alpha will equal to maximum. And then at sunset, go down here. Again, the alpha will be equal to 0. Okay, so will be the maximum value for alpha is 90 degrees. The minimum value for alpha is 0. They don't have negative value. They don't have value more than 90 degrees. Okay, but why I say at the overhead is not always 90. Let's say I look on the top view. This is the top view one. North, south, east, west. Top view one, so I can see your head only. So you are standing at the middle. Okay, I know that sunlight from east to west. Okay, but sunlight will go through path A or path B. Or maybe just go through the middle, path C. Okay, all of them are possible. This depends on the location. Okay, so if the sun pass through the path C and go to the west, then you will have the alpha equal to 90 degrees at solar noon. But whether you go through the A or B, then you won't get 90 degrees. Because you see that At solar noon, it means that sunlight will be here, overhead. But the problem is, it's not directly over your head. So you can see, still can see your shadow over here. This is your shadow. Okay? So that is not overhead. So you have the shadow, you have your own length, then the angle you measure is actually not 90 degrees. If the sun is on your overhead, supposedly you are not able to see your shadow. The shadow is directly on your feet. Okay? It won't extend out when it's overhead. Okay? So this solar altitude angle, some of the locations, let's say in Malaysia, Kuala Lumpur, 1 year, we only have 2 days where the sun passes through Palm Sea. Okay? Most of the time, the sun will pass through south of Malaysia. Okay, and then some of the day they'll pass through north of Malaysia. How I know that? Okay, then we go back to the declination angle. Which one is easier to explain? Okay, maybe I use this one. Maybe I can control. Okay, assume that Malaysia is at here. Kuala Lumpur lah. You see the red dot over here. We assume this is Kuala Lumpur, 3 degrees north. Okay, so the sunlight is on here. This is declination angle. And the sunlight also will move to downward. So the angle is 23.45 maximum. And here also same, maximum 23.45. So it means that if I take Earth as a reference, you can see that the sunlight will move 23.45 to the north of equator. This is what is the day? You can see that at the north of equator, the day should be June 21. And it moves down to here, middle. Middle we have after June, it will be September. Okay, after September, it will move down again. This is December 21. So December we have the summer on the North Hemisphere. Okay, and after December, it will go back here, March, and go up. It makes a cycle every year. Okay, so you can see that. Let's say on June 21. Okay, look on June 21 at this green line. You are standing in Kuala Lumpur. So this part is north of Kuala Lumpur. This part is south of Kuala Lumpur. And remember that when you look on the compass, it's follow the Earth's surface, not follow, don't like this, not like this, north and south, but you follow the Earth's surface. Okay, so it can be the curve going north and going south. So during the June 21, the sun is at your north. Can you see that? This green line is on the north of Kuala Lumpur on June 21. Okay, so that the sun will pass through the north of you. So the shadow should be fall at the south side on June 21. And then when the sun move until exactly on your top, which is here. Let's say the sun move under here, this point. I don't know when is the day, maybe early of September. Now it's exactly on overhead of Kuala Lumpur. So at that point, alpha will be equal to 90 degree at solar moon. Okay, or we call it Lahaina moon, or maybe you can call it a sub-solar one. There's another name for this value. Okay, and then other than that, you move down. Move down to December 21. December 21 is mean that now the sun is on the south of Kuala Lumpur. So the shadow should be on the other side. Okay, and then it will repeat to March and June again and again. So that you can see that when from June to September, you will pass through the Kuala Lumpur one time. Okay, and then second time, December, March. So from March to June, you will pass through the Kuala Lumpur for second time. So when you pass through the day, then you have an alpha of 90. Okay, so I can expect maybe early of September, or this one is after March 21. So maybe end of March or beginning of April. we have the alpha equal to 90 at solar moon. This only 2 days in Malaysia. Okay, what if your location is here? Let's say your location is quite north here, which is maybe 45 degree north. Okay, let's say your location over here, then the sun, the green line is maximum value on 23.45. So in other words, the sun is always at your north. Sorry, the sun is always at your south. You are standing here. Okay, the sun will move here, up, down, you don't care, but it's always at your south. So if your location is here, you have to point your solar panel to the south. If your location is bottom, then you have to face your solar panel to the north, because the sun is most of the time at your north. But then, how about Kuala Lumpur? Kuala Lumpur is in the middle, slightly above north. If you look on the day, which part will have more day? Okay, after this point, going up is the sun at your north. Before this day, going down, the sun is at your south. So if I look on this, maybe on the sun will be at the north of Kuala Lumpur maybe 40% of time, but 60% of time, the sun will be on the south of Kuala Lumpur. So if now I'm at Kuala Lumpur, my solar panel should face to the south. Okay, can follow? It should face to the south to get most of the sunlight, because this is the stationary system. Of course, if a sun tracking system, don't care because you always face to the sun. But if you want to find a optimum point to face, then we have to face to the south in Malaysia. But if you go to Australia, then other story, you have to face to the north. Okay. Digest a bit. Okay, so this explains why alpha is not always 90 degree at solar moon. We know that at one day, alpha will be 0 at sunrise and go up to maximum at solar moon and go down to 0 at sunset. But the maximum value is not always 90 degree. Okay, only 2 days in Malaysia have 90 degree. The rest will have the less than 90, maybe 70 something or 80 something. Okay, this is a solar altitude angle. Very easy to measure. Just measure the length of the shadow. Maybe you don't want to use human, you just can use a pen to put on the ground. As long as it's pointing upward, then you measure the length of the pipe, you measure the length of the shadow. You should be able to know the solar altitude angle. Okay. This you should be done this in experiment, but maybe you can do it at home. You can try later to measure. Okay, and then compare with the calculation. See whether how accurate is your measurement. Okay, then we have the declination angle, we have altitude angle. The third angle we need to learn is hour angle, H. Okay, this hour angle refers to the number of degree the Earth has to turn to bring the sun directly overhead. Again, in terms of degree, this actually is just the time. But the time is not follow 12 hour or 24 hour, but it follow the angle degree. Okay, so what is the reference point for our clock system? 12 a.m. midnight. Alright, 12 a.m. midnight is our reference point. So for 24-hour unit, we have 0. So that is the reference point. But for hour angle, this is to calculate sunlight. So 12 a.m. midnight is no sunlight. So what's the point? You take that as a reference. The reference must be very clear to notice. Okay. So for this hour angle, we take solar moon as a reference, maximum value as a reference. Okay. So something like this. Maybe I draw a bit. This is totally timer. Okay. But the reference point different. This point is 12 p.m. solar moon. Okay, but 12 p.m. here refer to the solar time, not the local time. Later I will explain more about what is solar time, what is the local time. But this 12 p.m. solar moon, then we draw a line. Okay, so here we have 1 p.m., 2 p.m. and whatever lah, okay? So here we have 11 a.m. Here we have 10 a.m. and until morning lah, okay? So solar hour angle always take the 12 p.m. solar loop as a reference. So at this point, hour angle equal to 0 degree. Remember that the measurement of hour angle is degree. So here at the middle, H equal to 0. And then how about 1 p.m.? 1 p.m. is afternoon. So we put the positive sign for it. And from solar noon, it is a 1 hour difference. Okay, 1 hour difference. If I want to convert to angle, how many angle? So you can see that one day we have 24 hours. Okay, and one rotation equal to 1 day, right? One self-evolve, the Earth evolve one rotation equal to 1 day. Okay, so that actually I can say one rotation equal to 24 hours. And one rotation is 360 degrees. Okay, equal to 24 hours. So 1 hour equal to 360 divided by 24. So I get 15 degrees. So now I convert hour to degree. So it means that 1 hour equivalent to 15 degrees. And after the solar noon, we give positive value. Before the solar noon, we give negative value. Okay, so 1 p.m. should be positive 15 degrees. Okay, the hour angle is positive 15. And 2 p.m. positive 30 degrees. And 3 p.m. will be positive 45. 4 p.m. positive 60. Okay, so on and so forth. Every 15 degrees. And then 11 a.m. Here is 0 degree. So here is a negative 15 degree. Here is negative 30 degree. So this is a reference as a hour angle. We just convert the time into degree, but we take the different reference point. For our clock, we take the 12 a.m. as a reference, but for our angle, we take 12 p.m. as a reference. But again, this 12 p.m. refer to solar time, not the local time. Again, can follow? So if you want to further get until the minute also can. 1 degree equal to 4 minutes, because you can see 15 degree. If I want to take 60 minutes, divide by 15 degree. So it means that 1 degree equivalent to 4 minutes. Also can, but if you don't care, we'll just calculate accordingly. Whether it's minute or hour, it can be a decimal point. Okay. This is our angle. I think should be easier. Okay, so our angle, we have the 0 value at solar noon. Okay, let's continue. We have 3 angles: altitude angle, declination angle, and hour angle. Then now the next one is the azimuth angle, jack. Okay, azimuth angle is the angle of the sun ray from the south or north. Sorry, let me answer a call. Okay, you also have the call to answer. Okay, let's continue. Okay, solar azimuth angle is the angle of the sun ray from the south or north. You can see here, I put south or north because I also don't know from south or north. It have to depends on your location and the time. Okay, if you have the negative value for angle to the east, which is in the morning, or before the solar node, and you have the positive value for angle to the west, which is after solar node. Okay, which is the negative 90 degree at sunrise and positive 90 degree at sunset. Okay, I think this one not really true. Okay, don't use this one, cross this. Because we are not able to measure until sunrise or sunset. So we just use 0 as solar node, correct? Okay, so let's say I give you an idea first. North, south, east, west. This is a top view on a ground. Okay, you are standing at the middle. Top view, so the sun is from the top. So this is the top view. And we know that sun move from east to west. Move from east to west. Okay, let's say the sun is over here. Okay, the sun move from east to west. So the angle between the sun and the north-south axis, we call it as the azimuth angle. Okay, but whether this angle is measured from the north or measured from the south have to depend on if the sun move from east to west through the south. Let's say the sun is over here, then the angle is from the south axis. This is that. Okay, so this is morning. So when the sun move until here, this is that. So it will give you positive value, but also refer to the north or south axis. Or here, also can. Everything refer to north or south. Okay, so this thing we also can do it experimentally. We just measure the shadow. Let's say same thing, north south axis. You are standing in the middle, and east and west. Okay, and let's say the sunlight is over here. What happened to the shadow? We are standing in the middle. You should have shadow over here. This is your shadow. Okay, so you can measure the angle between your shadow, and the north-south axis. This is the azimuth angle. But of course, the exact location is here. By a straight line, this is that. That exactly is the same lah. But if your shadow is on the south axis, so it should be opposite. Okay, don't measure exactly, but you have to take the opposite side. Okay, then it will be the Z. And of course, you need to define the north-south axis. You take out a compass, draw a north-south axis on the paper, and adjust accordingly. So north definitely refer to north, and you put a pen in the middle, and you have the shadow. Then you measure the angle here, then you know azimuth angle. Or you don't have the angle projector to measure the angle, you can use a length, measure the angle, length of the shadow, and the distance between the tip of the shadow to the north south axis. And you also can use sine theta, okay, sine z to find it. Okay, so this is how we measure the azimuth angle. Okay, you can see location 1, 2, 3, 4. Maybe I give you one example. Let's say at Kuala Lumpur, June. Location is Kuala Lumpur. And then date is June. So the sun the azimuth angle Z is measured from the north or south. Okay, we look back here. Okay, here. Okay, Kuala Lumpur over here. So at June 21, sun is over here. Okay, so the sun should be on your north. Correct? Can you see that? Kuala Lumpur is over here, and to the top is the north of Kuala Lumpur. So the sun is on the north of Kuala Lumpur. So in other words, the azimuth angle is measured from the north. Okay, not from the south. Okay, but on December 21st, then the azimuth angle is measured from the south. Okay, and then you can see that when you go up, when the sun is exactly at this point. Okay, angle is 0. Azimuth angle equal to 0, and that is solar noon. Every day it will become 0. Okay, so doesn't mean that at solar noon you will not see your shadow. Yes, you still see your shadow, but it's exactly on the north or exactly on the south. Okay, this we call it as a solar noon. So azimuth angle equal to 0. So we can see that we learn declination angle, altitude angle, hour angle, and azimuth angle. So that they of course have the relationship between them. So they come up with the equation over here. Sine z, sine azimuth equal to cos declination angle, sine hour angle divided by cos alpha. These four angles have the relationship to each other. Okay. So it means that if you know one, then you can find for the rest. And sorry, you need to get 3 to find the number 4. Okay. Okay, then this is a general geocentric system on the Earth. So we have hour angle. Okay, hour angle is referred to the solar noon. So we can see that this line is solar noon. Okay, and this point P is your location. Okay, so your location from the line for solar noon is hour angle. Okay, and then from your location to the equatorial plane, this is the latitude we put L. Okay, and then this one is from the plane to the location of the sun. We have the declination angle. Okay, you can see that the direction of sun ray to the declination angle to the equator line, we have the declination angle. But Z and alpha is on the surface, ground surface, or on the Earth surface. So we cannot see it on this. Okay. So then we have the one equation for this sine alpha equal to sine L sine delta equal to plus this. Okay. So from here you can get the altitude angle for any location. If you are given latitude, given declination angle and hour angle. Okay, and remember that L is latitude. So the L at the north hemisphere we give it positive value. The L at the south hemisphere we give the negative value. Okay, so that's the equation only valid. So I have to take note on this. L is negative for southern latitude. So Kuala Lumpur, you just put in 3.14 degree positive. Okay, like for Australia, then you have to put negative. Okay, so it's a general equation over here. And this about the sunrise and sunset. This is very important because you want to bring your girlfriend to see sunrise or sunset, right? So you need to know when is the time of sunrise or sunset. But of course, you can use Google nowadays. Maybe one day you are in the jungle, you can use Google, then you calculate that. Okay, so sunrise and sunset. So how we know that when is the sunrise, what time is the sunrise, and what time is the sunset? You can base on the equation that we learned just now. Okay, we come back to this equation. You can see sine alpha equal to sine L sine. This is the equation that we have. Okay, but for sunrise, remember sunrise, can you see the shadow line? The shadow line is infinity because the sun is at the same line as the Earth surface. Sorry, on your location, ground surface. Munjun, yeah, you can use hand without calculator to calculate that sign. Draw the graph. Okay. Sorry. Yeah. So alpha have the characteristic equal to 0 at sunrise or sunset. So you substitute alpha equal to 0 into this equation, sine 0. Okay. And then if you know the latitude is location. You know the declination angle, which is the day in the year. Then you can find the hour angle. Hour angle is referred to the time. Okay, so you substitute 0 here, then you can know what is the time of the sunrise and sunset. Of course, you should get two values, positive, negative, and these two values should be identical. In other words, let's say this is a solar noon. This is a sunset. This is a sunrise. The duration between the sunrise to the solar noon, I put AM, and the duration from solar noon to sunset, I call it B. Must be exactly the same for all location, for all time over the year. Okay? So that once we get the sunrise time, which is hour angle, as the hour angle, take the solar noon as a reference. So you should be able to get the sunrise time or sunset time. And once you get one, you should get the second one. Okay, because this duration is totally the same. Okay, let's say I get the hour angle is 60 degree. Let's say I calculate alpha equal to 0 and I get H equal to 60 degree. So it means that from solar noon to sunset is 60 degree. So I divide by 15, so it's 4 hours. So here's to be 4 p.m. Okay, because 60 divided by 15 is 4 hours short. So solar noon to here, solar noon is 12 p.m. So I know that it's exactly at 4 p.m. And at sunrise, is to be minus 4 hours. 12 p.m. minus 4 hours, I get 8 a.m. So I know that sunrise and sunset. Sunrise is 8 a.m. in the morning, and sunset is 4 p.m. in the afternoon. Okay, but of course, this is just a reference, not 60 degree. You can calculate from Malaysia whether it's 60 degree or 120 degree. Okay, so from here we can get the hour angle. Okay, the equation no need to remember it. That the concept is still used back the same equation over here. Okay. And other than sunrise time and sunset time, we still have the day length. Day length is the duration from sunrise to sunset. Day length, how long is the day? Okay, so it should be from sunrise to sunset. So just 4 p.m. minus 8 a.m. So I have 8 hours of day length. Okay, so the day length is 2 times hour, correct? Okay. Yes, maybe you try one example. Determine the sunset time and day length today at TAUC Kuala Lumpur. This is your task. I'll give you a few minutes to answer this. Remember, you can see that sunset time, I put LST, local solar time, because whatever we calculate in this equation, all refer to the location of the sun. Supposedly, the time is referred to the location of the sun, but every country make a slight adjustment. Because every location, let's say I am at this location A, and location B is just 10 meters from me, but actually my longitude already slightly different. But different location, you want to use different time, all right? So that we centralize, we generalize. For Malaysia, we have this time. For Japan, we have another time. So entire country have the same time zone. So that the actual time and the local time made by the country is different. Okay, so I have the specific over here. This refers to the local solar time, not the local time appear on your watch, on the clock. Okay, so now we calculate the sunset time. I give you 5 minutes. Today, so you have to use the date today, 7th of July. Okay, so let's do it together lah. Sunset time. So we have to refer to the equation from here. Okay, so we can copy down the equation. I think you did write down. Okay, sine alpha latitude sine declination plus cos L cos declination angle and cos R angle. Okay, so I know that at sunrise or sunset, alpha equal to 0. Okay, alpha is 0 because shadow length is infinity. So that alpha equal to 0 degree. And I need to find L and declination angle so that I can get the H. So the L from here is given. Latitude is the first one, north or south. We call latitude. And 101 is a long medium. So latitude is 3.2162 degree north. So I need to put the positive value. Okay, and then declination angle, you can just refer back to the equation. The 3.45 send this value. Okay. Then 3.45. Okay. So now what's the problem? What's the number of n? Anyone give me the answer? 7th of July is what value? Remember, the number of n is calculated from the 1st of January. 1st of January is 1. 31st of December is 365. So how about 7th of July? You can type in the chat box, tell me the value. $182. Okay, so let's calculate. January we have 31 day, February 28, March 31, April 30, May 31, June 30, July 7. So this is how we calculate that. $188. Okay. So we have 188. So use n equal to 188. Zhongyi, try to calculate why you get 182. Maybe some of the case, let's say the date is on December or November. So actually you can calculate from behind, or else every month you calculate, you may confuse. Okay, you may calculate from behind. December minus 365 minus how many days? So what is the declination angle that you get? $22.59. Okay. $22.59 degree. Okay, then once we have angle, we have everything. Okay, maybe we check the result. Declination angle, you get 22.59. We go back to the equation graph over here. This is very good. Now you can do this to check your result in the exam. Then on the graph, 22.59 or maybe 188 day. Okay, 188 maybe here. Okay, I think quite close. Okay, I can see you draw 188, draw out you exact, you can estimate agak-agak the value around 20 lah. So we get 22.59 is okay lah. If I mean that if you draw the line, you get positive value, but your answer is negative value, and then something wrong. Check the answer. Okay, if you are not confirm that answer is correct, sorry, if we are not tell you how to calculate, but it will give you the estimated value over here. The function of the graph normally will not give you the exact value, but give you the estimated value. Agak-agak lah. Okay. So we have 22 point. Then you can substitute all of them into the first equation. So we have sine 0, sine 3.2162, sine 22.59, cos and cos h. So now I want to find h. Give me in terms of degree first before we convert to hours. Negative 91. Are you sure? Okay, you can get either positive 91 or negative 91. But if you get negative 91, it means that you are getting the sunrise time. You can get both lah, positive or negative. Okay. So if I calculate, I get positive value, I don't need to do so much conversion. So I get 91.34 degree. Okay. So once you have 91.34 degree, now I want to convert to hour. So I put H, H sunset, capital H, so should be 91.34 divided by 15 degree. Because I want to convert back to hour. So I get 6.0893 hours from solar moon. So what is the exact time? Okay, so you can write in time. So should be sunset time. Should be 12 p.m. Sorry, 12 hours now. Okay, we put 12 p.m. because we want to convert we want to change the reference point from 0 to 12, so we put 12, solar to 12, plus 6.0893 hours. So should be 18.089. Or we seldom put it in hour form, decimal form, so you convert to minute. So I have 18.05.02. Sorry, 21. Enough lah, minute, hour, minute. Or 6:05 p.m. Yeah, correct, 6.05. No need to do so much conversion from decimal point to hour minute, you can always use your calculator to do the conversion. You can see that in your calculator there is one button, something like this, comma, sorry, full stop, comma, comma, comma. You find the button over here, this kind of button. Okay, you press it, then you will convert from decimal point to hour minute or hour minute to decimal point. So we get 6.05 p.m. Okay, so if you want to convert back to sunrise, because this one it asked for sunset already, of course I don't need to show sunrise. So if we want to sunrise, it means that sunrise should be 12 minus 6.0893. You can do the same thing. So it's 5.91, or if I convert to hour and minute, it should be 5.5438 a.m. This is the sunrise time. Okay, so how about the day length? The question asks for day length. So day length equal to 2 times the sunset hour. So you just take, where to write? 2 times 6.0893. So the day length for Kuala Lumpur today is 12.1786 hours. Of course, you don't need to put so many decimal points. 2 decimal points in the exam screen. Okay, but when you want to put 2 decimal points, final answer need only 2 decimal points. But before that, try to not round up. You can use all the values from the calculator. Okay, but when you write down, you just write the 2 decimal points. Okay, so to ensure that the accuracy of the result. Okay. Any problem to calculate the sunrise, sunset time? But you see, the sunset time is 6:05 p.m. And I think all of you know that in Kuala Lumpur, we will never have sunset at 6 p.m. Normally it's 7:30 or 8 p.m. we already have sunset. This is because the difference between local time and the solar time. This one I will teach you next classes. Okay, any question at this point? You digest a bit. This is the
No question, sir.
Okay, very good. Then we can dismiss now. So this is a recorded lecture, so you can refer to the recording if you need any revision. Okay, so I think that's all for today. Thank you so much, and see you next classes. And again, for Army and RMH, we have lab starting from this week.
Sir.
Yeah. Any question, you can stay back.
Just want to confirm. So later 2 p.m. for RMH, no lab lah. It's tomorrow, right?
RMH have lab today. Not in my timetable. Tomorrow 2 p.m. or today 2 p.m. Can we?
Yeah, let me check again.
Yeah. Okay. Announce it tomorrow. Should be tomorrow lah.
Oh, tomorrow. Sorry.
Yeah. So tomorrow 2 p.m. Yeah, I said today 2 p.m. Maybe. Okay. 时间. Oh, Wei Shen. Sorry. Maybe I missed it just now. So it's tomorrow for RMH and Friday for RME. So
okay, thank you, sir.
Okay, thank you, Wei. Thursday you should consider to build a new one, because the existing dam should be for certain things. Unless the existing dam is not for the power plant, then it's possible to propose to modify. It's okay. Okay, but I'm afraid that the cost of modification is a bit difficult to get. Rather than you build a new one, you can get the information easily from the internet. Okay, that's it. Okay, if no more question, then that's all for today lah. So see you next classes. Bye bye.
Thank you, sir.
Okay, thank you, Vincent.
Thank you, sir.